Thanks for the introduction. My name is Xunjing. Today I'm going to present our paper, TensorCrypt, Repurposing Neural Networks for Efficient Cryptographic Computation. This is a joint work with Professor Siqing Ma and Professor Zhichang Lin. At the very beginning, I want to emphasize accelerating cryptographic computation is very important. So imagine we are in a virtual meeting. For example, we use Zoom. Then there are maybe 50 attendants. And in Zoom, in Zoom, they have the capability of end-to-end encryption for the data. So for 50 participants, it requires encryption and decryption of 5 megabytes per second, meaning that, for example, if we use AES for this process, AES is a block cipher. It requires to process about 260K blocks per second. It's a huge amount of data. Then in this paper, we focus on accelerating cryptographic computation by repurposing neural networks. If we look into existing works, we can find there are several categories. For example, the instruction set-based acceleration approach, like ASNI dedicated for Intel CPU. And also there are GPU and FPGA-based acceleration approach. However, there are some limitations. First, those solutions require diverse hardware and software sets. And often, they tend to leverage the hardware capabilities without much software optimization, leaving their approach to kind of suboptimal. And also, this makes the software development process very complicated. At the meantime, we are in the era of large language models, and we see the neural networks can be very promising. And more importantly, neural networks are generally supported by diverse software and hardware stacks. For example, there are hardware accelerators from NVIDIA and Google. Also, they can be deployed into diverse hardware platforms. For example, they can even be run on the IoT devices. And also, there are a lot of AI or deep learning frameworks. For example, the popular ones include PyTorch, TensorFlow. And another key feature is those neural networks are compiled and optimized by compilers. For example, TVM, XLA. And if you use those AI libraries to run your neural networks, you can leverage them in different programming languages, meaning that neural networks can be deployed in the diverse scenarios and the platforms. And last but not least, neural networks are Turing complete. This has been proven. However, think about our objective, which is to accelerating cryptographic computation using neural networks. One intuitive idea is that why not we just train a model for it? The answer to it is it's very challenging. If you look into the SOTA models, for example, XAI has Grok 3. If you use it for any like some complicated crypto computation, you will find that the computation basically is wrong. If you compare the ground truth ciphertext with the one produced, the key reason is that so first the neural networks, the training-based approach usually requires a lot of data, but in the cryptographic computation, there are a lot of nonlinearity. And also the input-output space can be infinite, meaning that you cannot enumerates all the input and output to train the model. So based on this observation, we avoid using the training-based approach, but our insight is maybe we can directly leverage the capability or property of computational graph. So basically, neural networks are computational graphs. And at the same time, more importantly, cryptographic computation can be represented as computational graph as well. So why not we directly combine them? And the computational graphs are composed of tensors, which could be the input and output value, or the intermediate value. There are also operators, which can be the mathematical operations. Then we can, for example, build the graph for different computations. For example, the linear one, if we set the input x1, x2, and y as a floating point number, you can just build a model for floating point number addition. You can even build a more nonlinear computational graph. Based on this observation, we have proposed TensorCrypt, which is a framework to transform cryptographic computation into neural networks. At the very beginning, we have abstracted the domain-specific, we have abstracted the crypto computation and the neural networks into domain-specific languages. Also, we propose the transformation rules. We basically divide the problem into two layers. At the program layer, we try to transform the whole program into a neural network. And then we divide the program into individual statements and then use the program transformation to transform the statement into neural network layers. And also, we have designed semantic rules. Due to the time complexity, I won't go through them one by one. Based on the transformation framework, we have very formal proof. We basically prove that our transform neural networks does not leak additional information to attackers, meaning that the transformation source and the target are in the same semantic level and in the same security level. In addition to that, we have proposed model optimizations. Here we have operator fusions to fuse the cryptographic computation. And this process helps us to reduce the overhead, including the overhead at the data transformation and also the operator scheduling. In addition, we have another optimization, which is load on use management. Our key observation is that existing, for example, GPU-based acceleration, if you look into its step, it follows this pipeline. So at the very beginning, the data is moved from CPU to GPUs. And then there are three individual crypto computation performed. And finally, the ciphertext is moved back to CPU. However, we observe that in this process, the counter is loaded at the step 1, but it's only used at step 4, meaning that if you look into the GPU profiling, you will find that there are a lot of memory swapping process because the GPU has to swap the memory for the computation, but the ciphertext occupies a lot of memory. For load on use memory management, we have a simple but effective approach. We basically load the counter when it's used. For evaluation, we have select 3 ciphers, including AES, ChaCha, and SOSAR. I want to emphasize that ChaCha and AES are the only 2 ciphers selected in TLS 1.3 for large-scale volume data of encryption and decryption. For the baselines, we have those 2 baselines. First, they are available. Their implementation are available. And also, we check their correctness using the test vectors. And more importantly, they are popular and most effective ones. For evaluation, we have tons of evaluations. The first evaluation is about effectiveness. Our evaluation have proved that TensorFlow models are up to 5.4 times faster than the baselines. We also break down the overhead to see whether our optimization are helpful or not. They are effective due to the time limitation. I omitted them. You can refer to our paper. Another key evaluation is about the deployment scenarios. As I said, the neural networks are supported by diverse software and hardware platforms. We deploy the model on NVIDIA GPU, Google TPU, and we also deploy them into cloud environment. For example, desktop, Google Cloud, Google Cloud, and also we deploy them into desktop, laptop, and also smartphone IoT devices. We have also compared the deployment for encryption and decryption, or we see some kind of symmetric efficiency. To conclude, in this paper, we are the first to repurpose neural network for effective cryptographic computations. And we propose a novel program transformation framework with domain-specific language and model optimizations. And also our evaluation shows advanced efficiency with diverse software and hardware stack deployment. That's all for my presentation. I'm happy to take any questions.
Thank you. I really respect the work which contains a lot of dedicated implementation. Mm-hmm. Yeah. Any questions?
Go ahead.
Sorry. Thank you.
Very interesting work. My question is, so you basically proved that this, in terms of security, so it will not weaken the original cryptography security, right? So they're equivalent in terms of the security proof. Is they're equivalent to their original design, right? I'm asking because we were seeing many cases that, some minor changes to the protocol design, cryptographic protocol design has already led to fatal disasters, right?
Yep.
So I just want to make sure that's very important. Yep. So do you think that's gonna change the security proof, or is the same as the original design? Because previously we consider the security from the only those, right? So those popular computations, right? Right now we have the additional layer, right? This neural network. Do you think that will add a bit of ambiguity to the security and also open up like other attacks, right? So side channel attacks or other the neural network specific attacks to the cryptographic design. Do you think that's also possible?
Awesome question. So first, basically the design I proved at the same security level, but the implementation are different. So that's one of your question. The second question is, for example, side channel. So in our paper, we have acknowledged that they can be attacked by side channel. So like timing side channel. Also, since we achieve crypto in neural networks, a intuitive question is it secure in terms of adversary machine learning attacks? So our answer is those adversary ML attacks cannot be applied to our model because those attacks can be applied to learning-based approach. But for us, we directly construct the crypto cipher using computational graph. Yeah.
So you have to translate their design from your neural network-based design, or do you think it's possible that we can, directly design cryptographic protocols in the future using neural networks? You don't have to do that translation in the middle. Do you think that's possible?
Yeah, I think that could be a very interesting future work. Yes.
Thank you.
Thanks for your question. And thank you.
Hey, thanks for the great talk. I'm just trying to understand, how does the evaluation compare against like AES and I? You mentioned that at the start. So how does this compare with AES and I? Yeah.
Oh, in our paper, we have, so first, when we select a baseline, we want to have the save our performance. ASNI is not. So our baseline has been proved to be more faster than the ASNI.
Oh, it is actually faster than AES and I with this neural network-based mechanism?
No, the GPU-based baselines, they are faster.
Okay.
Yeah.
Thanks.